Okay. The last class we have seen, the concept is called as counter. Okay. The counter is nothing but, for example, I am saying that it is a 2-bit counter in the sense, what is the meaning is, the counter is associated with two consecutive flip-flops. Okay, that is called as a 2-bit counter. And then we have seen, so what is the application of 2-bit counter? The application in the sense it will count the clock pulse. That is the application. So what is the application of counter in the sense? Count the clock pulse. So where we are going to use that counter in the sense if we consider your machine. Okay, for example, user you are going to provide input to the machine, and then what happen? This is the input for your CPU, and then finally it's going to produce it as output. So in order to produce it as output, what happen? Your CPU is going to use number of devices. Okay, for example, hard disk is one of the devices. Similarly, n number of devices are available in the CPU. So in order to operating all the devices, we needed the clock pulse. So proper functioning of each device in the CPU, it's require clock pulse. In the scenario, counter what it's going to do, it's going to count. For example, for example, the one of the counter is associated with the hard disk. The counter what it's going to do. So in order to function, in order to generate the proper output, how many number of clock pulse it's going to take? That task is carried out by counter. Okay, that is one of the application. The counter otherwise called as a um, the counter otherwise called as a divided. It called as the frequency divider. The counter otherwise called as a frequency divider. So after that, we have seen what are the different ways we are going to implement the counter. So in order to implement the counter, we are using two types of flip-flop. One is called as a JK flip-flop. One is a JK flip-flop. Another one is called as a T flip-flop. Okay, another one is called as a T flip-flop. Okay, so what is the truth table of JK? Okay, J and then K. What is the next state? Okay, this is a next state is nothing but 0 0 in the sense it will retain the previous state, 0 1 in the sense the output 1 equal to 0, and then 1 0 in the sense 1. Suppose 1 1 in the sense it's a complement of the previous state output. Okay, this is a state. This is a truth table for JK flip-flop. And then after that we have seen what is the design diagram for JK flip-flop. So whenever we are going to provide, we are going to implement within the, whenever we are going to implement the flip-flop within the counter, what happens? The default input for JK is called as a 1. So why the default input is 1 in the sense? 1 in the sense, okay, if we consider any T flip-flop, it is also accept input as a 1. I will tell you why it is a 1. Okay, for example, 0 in the sense it will retain the previous state. 1 in the sense what happened, it will complement of previous state. Okay. So why the input value equal to 1 in the sense, I will tell you. Okay, 1 and then it going to produce a 2 output. One is called as a Q and then Q1. So why in the sense what happened? Suppose it always take input as a 1. So if we look at the table. So whenever the input value equal to 1, what happened? It will complement the previous state output. Okay. You should remember all the things. And then I'm going to begin with how we are going to design 1-bit counter, 2-bit counter. Let's see one by one. Okay. And then one more thing I want to tell that suppose in your counter you have n bit in the sense how many number of states are available in the sense, how many number of states are available in the sense 2 power n states are available. 2 power n states are available. For example, in this case, here Here, how many number of variables are there? That is nothing but 2. So 2 variable otherwise called as a 2 bit. How many number of input combinations are available? 4. So n equal to 2. What about number of state in the given counter in the sense 4? So what are those 4 state in the sense 0 0 0 1 1 0 1. Suppose n value equal to 3 in the sense what is the meaning? 2 power 3. 2 power 3 in the sense 8. Okay. Okay. You should remember those concepts. Okay. Okay. So now what I've done, I'm going to designing single bit, 1 bit counter. Okay. I'm going to designing 1 bit counter. Okay. In order to designing the counter, okay, you can take any one of the flip flop, either JK flip flop or T flip flop. In my example, I'm going to consider JK flip flop. Okay. JK. So what is the meaning of 1 bit counter? Only 1 flip flops are available. That's why it's called as a 1 bit counter. Okay. What is the value of J? What is the value of J? 1. What is the value of K? 1. Okay. Already we have seen 2 different type of counters are available. One is called as a synchronous counter. Another one is called as asynchronous counter. So what is the meaning of asynchronous counter? Anyone tell me? What is the asynchronous counter? So asynchronous in the sense, for example, number of flip flops are available, and then each flip flop what happen, it going to accept different clocks. For example, first clocks, what happen? I'm going to provide one clock. In second flip flop, what happen? The output of the first flip flop as input for second flip flop. This is the output is acting as clock for next flip flop. Similarly, the output of second flip flop clock for next flip flop. If it is that is called as asynchronous. Okay, here first we talk about asynchronous and then we go for synchronous. Okay, this is called as a asynchronous counter. The asynchronous counter otherwise called as a ripple counter. So why it is called a ripple in the sense? The output of the previous stage input for next flip flop clock cycle. That's why it is called as a ripple counter. Okay, it is called as a ripple counter. Okay. Now what happened? We are going to designing 1 bit ripple counter. The ripple counter otherwise called as a asynchronous counter. Okay. Let's see how do you designing it. Okay. Okay. So in order to functioning the flip flop, already I said it's required the clock pulse. Here what happened? I am providing clock pulse as negative clock pulse. Okay. So whenever we are going to talk about the counter, in order to explaining those functionality, we are using for timing diagram. Okay. I will tell you what is a timing diagram. For example, this is a clock pulse. Okay, so what is the meaning of clock pulse in the sense? Then only what happened, your flip flop it can able to work. Here, what type of clock pulse we are providing a negative clock pulse. So what is the meaning is whenever the negative edges occur, then only what happened, the particular flip flop is working on. Okay, okay. For example, now initially what happened? So initially what happened? If you consider that flip flop is associated with the 2 output state, one is called as a Q, another one is called as a Q bar. In initial state, okay, for example, our consideration, the initial state of the flip flop is called as a 0, 1. Okay, sir, you can take in reverse order also, there is no problem. So, for example, here instead of 1, okay, 0, what happened? You can take it as a 1. Okay. So this is a Q, this is a Q bar. This is 0 in the sense, definitely Q bar value equal to 1. Suppose the Q bar value equal to 1 in the sense, definitely the Q bar value equal to 0. Okay, that is the assumption. For example, this is a Q bar. For example, okay, for example, whenever the negative edges occur, that time only what happens, the state of the flip flop it will change. The state of the flip flop it will change. For example, what is the initial value of q? For our assumption, 0. So whenever the negative edge, this is called as a negative edge. Whenever the negative edge is occur, what happen? Okay, what happen? The state of the flip flop it will change. The state of the flip flop it will change. Okay, for example, so if in the counter point of view, all the flip flops, JK and then T flip flop. So make use of the two flip flop only. We are going to implement the counter. In each of the flip flop, what it's going to do? Suppose the previous state input is 1 in the sense what happened? It will complement the previous state. So what happened? The current state output is 0. Suppose the previous state input is 1 in the sense the current state output is 1. So it will what it's going to do? It's going to perform toggle operation. Toggle in the sense complement operation. For example, in our case, what happened? The previous state output is 0. So what happened? It performed toggle. Toggle in the sense complement. So up to which it will retain same state in the sense when it will encounter the next negative edge. Here only what happened? The next negative edge is occur. Whenever the negative edge is occur, what happened? It will change the value. So change the value in the sense this is a previous state. The previous state value equal to 1. Okay, when the negative edge is next negative edge is occur, what happened? It will change the state value. The previous value is 1. Now what happened? It will change the value equal to 0. So okay, again up to which it will retain the value is 0. Whenever there is next negative edge is occur. So here the negative edge is occur. So again what happened? It will toggle in the sense. Okay, it's a complement of the previous state value. Okay, so okay. This is nothing but what I am trying to say that it is the functionality of JK flip flop I can explain using timing diagram. Okay, same thing I will explain using the truth table. For example, initial clock cycle. I am not providing there any clock cycle for the flip flop. So it is a previous state of the flip flop. So Q value equal to 0 and then Q bar value equal to 1. So first what happened? I am going to provide the first clock cycle. This is a negative clockage. Okay, if provide in the sense what happened? Okay, it will double. Previous value is 0. What happened? Okay, it make it as a 1. Okay, so this is a Q bar. So what is the Q value? 1. So this is a 0. Next, what happened? I am going to provide the next clock cycle. So what happened? The previous value is 1. What happened? It make it as a 0. This is a Q bar. What is the Q value? 1. Okay. So this is so same thing I can explain it here in the timing diagram. Okay. Okay. So after the end of the clock cycle, what happened? After end of the second clock cycle, what happened? It will retain same state. Initially, in the state of the array state, what happened? It's going to retain. Okay, this Q otherwise called as a up counter. I will tell you why it is called as up counter. This is called as a down counter. Okay. So already we said counter is going to perform counting operation. Okay. For example, what are the two different types of counting? One is nothing but increment counting. Another one is called as a decrement counting. The increment count otherwise called as a up counter. The increment count otherwise called as a up counter. The decrement count otherwise called as a down counter. This is called as a down counter. So I will tell you why it is called as increment. So for example, what is the value of Q? Initial value is 0. Next one is 1. Again 0. So based on that, what happened? I am going to write the state diagram. Initial value is 0. Next what happened? The values are increased to 1. Again what happened? Again the values are decreased. So the values is keep on increasing, 0 and then 1, again 0, again 1. So that's why it's called as a up counter. That's why it is called as up counter. And the next you consider the Q bar. What is the value of Q bar? Initial value is 1. Next decrease, again 1. So initial value is 1 Next, the values are decreased. Again 1. Okay, again decreased. That's why it's called as a down counter. Okay. That's why it's called as a down counter. The Q bar also, what I'm going to do, I'm going to represent it here. The initial value is 1. The whenever the next positive, for example, this is a negative edge sucker, what happens? Okay, the value make is a 0, and then it will retain up to next negative edge sucker. Okay, here negative edge sucker, what happens? So it will maintain it will double the previous value. This is 1. Okay, so 0, this is a 1 and 0. Okay, so same thing, we will got it 1, okay, and then 0, and then 0, 1. Okay, this is called as 1-bit counter. Do you have any queries regarding this? Do you have any queries?
No, sir.
Okay. Okay. Okay, this is called as a 1-bit counter. The 1-bit counter otherwise called as modulo 2 counter. This is called as a 1-bit counter. 1-bit counter otherwise called as modulo 2 counter. I will tell you what is the meaning of modulo 2 counter. Okay. Here I will tell you, sir. Look at that. Here, what is the meaning that here 1-bit counter. So n value equal to 1. Okay, how many number of states are available? 2 power n. So 2 power 1 in the sense 2. So what is the meaning is state. If we consider this diagram, how many number of states are available? Only 2 states. 2 state. One is called as a 0 or 1. Okay, so here this is called as mod 2. So this is called as a mod 2 counter. Mod 2 counter in the sense, otherwise called as a 1-bit counter. Why it is called as a mod 2 counter in the sense, it containing 2 state, either 0 or 1. That's why it's called as a mod 2 counter. Okay, it's okay for you. So what is it mod 2 in the sense? The maximum number of or maximum possible state in the counter is 2. That's why it's called as a mod 2 counter. So one more name also is there, that is called as divide by 2 counter. Divide by 2 counter. So I will tell you why it is called as a divide by 2 counter. Okay. So as of now, do you have any queries?
No, sir.
Okay. So normally, suppose I am going to say one clock cycle. So one clock cycle, it indicates the one positive edge plus one negative edge. We call it as one clock cycle. Okay, if we consider this diagram, okay, if we consider this diagram, what happened here? What happened? This is I call it as one clock cycle, because here one negative edge is there, one positive is there. That's why I'm going to call it as this is called as one cycle, one timing cycle. Okay. Next, you consider this one. Consider Q. This is one positive edge, and this is one negative edge. Okay, this is one negative edge. Up to this, we call it as one cycle. Up to this, okay, here up to this we call it as one time cycle. Up to this we call it as one cycle. So, okay, this is a timing diagram, okay, up to which we call it as one clock cycle. This is I'm going to represent it as a 2t. Sir, why I'm going to represent as a 2t in the sense? Compare with the previous cycle. So, this is a one clock cycle. Again, on here, one more clock cycle is there. So, both of the period we call it as one clock cycle. So, that's why I'm going to represent it as a 2t. Okay, that's why I'm going to represent it as a 2t. Um, okay. Sometimes the people called as the counter, otherwise called as a such way that they are going to represent it. This is a counter, for example, counter. This is a mod 2 counter. So mod 2 counter. So mod 2 in the sense what happen? It's going to produce a 2 output, either or 0 or 1. Suppose you are providing input as a frequency in the sense, suppose you are going to provide any frequency in the sense. The what is the output frequency in the sense? F divided by n. Okay, F divided by n. Here n will equal to 2, so F divided by 2. So that's why it's called as divided by 2 counter. The what happened? The frequency is divided by 2. That's why it is called as a divide by 2 counter. That's why it is called as a divided by 2 counter. Okay, it's okay for you? It's okay for you?
Yes, sir.
Okay. First, கொஞ்சம் starting அப்படி தான் இருக்கும். போக போக hereafter we will see different type of counters, 4-bit counters. We will see that. If we go through more example, you will get some clear idea. Okay, and then okay, the frequency they will defining as like that. So the frequency is nothing but 1 divided by t. Okay, okay, you want to know the frequencies are nothing but 1 divided by t. Okay, we will see some example, you will get some clear idea. Okay, this is a 1-bit counter. Next I am going to talk about 2-bit counter, 2-bit up counter. Okay, next one is called as okay, 2-bit up counter. Up counter, and then implement using negative edge trigger. Negative edge trigger. Okay. So what is the meaning is? So what is the meaning? So here n equal to 2. So what are the how many number of possible states are available here? 4 possible states are available. Okay, 4 possible states are available. So n in the sense 2 flip-flops are available. So make use of that. We are going to generate 4 different state, 4 different output. Okay, in order to implement that 2-bit up counter, what happen? I'm going to take 2 JK flip-flop, J and K. Okay, so initial value of J and K is nothing but 1. So now what I'm going to do, I'm going to provide negative clock cycle. I'm going to provide negative clock cycle. This is a ripple counter, ripple carry counter. So what is the meaning of ripple carry counter? So ripple carry counter otherwise called as asynchronous counter. What is the meaning of asynchronous counter? The output of the first flip-flop, it's acting as input clock cycle for next flip-flop. Okay, that's why it's called as asynchronous counter. So here J value, this is the first flip-flop, that's why I'm denoted as a 0. This is the second flip-flop, that's why I'm going to denote it as a 1. Okay, what is the initial value of J and K? This is a 1, this is a 1. So what about output? The Q1 and Q1 bar. Okay, this is the output. Okay, this is the output, this is a clock. Okay, normally what happens, the first flip flop in the counter, always the first flip flop provide output of LSB. The second flip flop provide output of MSB. Okay. Okay, listen. Okay. So now what I'm going to do, I'm going to write the truth table of 2-bit up counter. Okay. So first of all, I'm going to provide the clock pulse, and okay, this is, so already I said this is called as first flip flop we produce LSB. Okay, this second flip flop is going to produce the same. Okay. So I'm going to write the output. How we are going to write the output? From LSB to MSB. Okay, this is LSB. So here what happened? Q1 and Q0. Okay, next. Okay. And then, so what are the two output it going to produce? One is called as a Q. Another one is called as a Q bar. So that's why I'm going to write two parameters, Q1 bar and then Q0 bar. Okay. For example, in our case, initial state. First, I'm going to write the initial state of both flip flops. So initial state, for example, Q0 equal to 0 and then Q1 equal to 0. So what happened? So Q complement. So if Q0 equal to 1 in the sense, Q0 bar equal to 1. So Q1 equal to 0 in the sense, Q1 bar equal to 1. This is the initial state of those flip flops. Suppose what happened? First, I am going to provide the negative clock edge. So whenever the negative clock edge provide, what happen? Okay. So what happen? What it going to does? Whenever the negative clock edge I am going to provide, what happen? So what is the previous state of the flip flop? This is a 0. So what happen? It's going to perform double. Double in the sense the complement of the previous state. That is called as, we call it as a double. So 1. So what about Q0 bar? The Q0 bar is nothing but 0. Okay, this is a 1. Okay, the 1 is it going to produce. So this is the input for next clock pulse. So you want to remember one more thing. One is called as positive edge trigger. 0 is called as a negative edge trigger. Okay. So 1 is a forward to here. This is a input clock pulse for this flip flop. This is a negative edge trigger. So 0, the input value equal to 0, then only what happens is going to operate. Suppose the input value equal to 1, in the sense what happens, it does not perform any operation, it will retain the previous state. Okay, what is the previous state here? So what is the previous state here? The previous state is a 0. So what happens? It will retain the previous state. It is okay for you? It's okay for you?
Yes, sir.
So once again, I'm going to tell that the initial state of the flip flop is nothing but 0, and then Q bar is nothing but it's a complement of Q. So that's why I'm written as a 1. First, initially, what happened? How it going to react the first flip flop in the sense? If you consider the first flip flop, it will react for every clock cycle. It will react for every clock cycle. Whereas in the second flip flop, what happens? It will react only negative edge trigger alone. It will react only negative edge trigger alone. So for example, I am going to generate the output is what is the output of first flip flop in the sense 1. This is the input for next flip flop. This is acting as a clock. 1 in the sense, what is the meaning is it's a positive edge trigger. So it does not perform any operation and retain the previous state. That's why I'm going to write as 0, 1. So next what happen? I'm going to provide a 2. I'm going to provide the clock pulse as a 2. Second clock pulse, what happen? So what happened? What is the previous state? Already I said the first flip flop what happened? Every clock pulse what happened is going to perform some operation. The previous value equal to 1, then now the value equal to 0. So what is the complement? This is a 1. Okay, what is the complement? This is a 1. So now what happened? I'm output is 0. This is the input for here. This is the input for here. Now what happened? Now it will get the input as negative edge trigger. What happened? It's going to function in it. So what is the previous state? The previous state is a 1. Previous state is a 0. What happened? It performed double operation. So 1. So here 1. What is the value of Q bar? 0. Okay, next I provide the third clock cycle. The third clock cycle, what happened? The first flip flop is going to react. So every clock cycle, what happened? It's going to perform operation. Okay, this is a 1, this is a 0. So this is the input for 1 is the input for the next clock cycle, next flip flop. So 1 in the sense what happened? It will retain the previous state. This is a positive edge trigger. So when you are going to provide the positive edge trigger, it does not perform any operation. That's why it will retain the previous state. Next what happened? I'm going to provide a fourth clock cycle. The fourth clock cycle, what happened? Okay, this is a 0. Okay, 0. Here 0. Okay, this is the input for here. So now what happened? It's going to react. So what is the value of Q1? Q already previous values are 1. Now what happens? 0. This is a 1. Okay. Okay, this is a functionality of 2-bit counter. So same thing, what happened? I'm going to represent it as a timing diagram. Before more to the timing diagram, what happened? I'm going to draw the state diagram. So state diagram for Q1 and Q0. Okay. So what is the initial state? 0, 0, 0, 0. We call it as 0, 0. We call it as a 0, and 0, 1. We call it as a 1, and 1, 0. We call it as a 2, and 1, 1. We call it as a 3. So initial state is a 0, 0. So that is a 0. Next one is 0, 1. 0, 1. We call it as 1. So next, what is the next state? 1, 0. That is called as a 2. And then 1, 1 is called as a 3. Again, what happened? Okay, again it will reduce to 0. So this Q1 and Q0 we call it as up counter. It provides a functionality as a up counter functionality, whereas the Q and Q bar, Q1 and the Q0 bar, is going to provide functionality as a down counter. I will show you. So what is the initial state? The initial state is a 1, 1. 1 is nothing but 3. What about 1, 0? 1, 0 is nothing but 2. What about 0, 1? 0, 1 is nothing but 1. Okay. What about 0? 0, 0? 0, 0 is nothing but 0. Okay. Again, it will retain same state. So it will decrement the value. That's why it's called as a down counter. Down counter. Okay. So it will provide functionality as up counter. And then it will provide functionality as down counter. Down counter. Okay, do you have any queries? So do you have any queries? So why it is called as a down counter? Why it is called as up counter? In the 2-bit up counter, it going to provide two functionality. If we consider Q point of view, it acting as a up counter, and then Q bar point of view, it's acting as a down counter. So do you have any queries?
No, sir.
Okay. So same thing what happened, I'm going to represent it in the timing diagram. Okay. So I will show it in the timing diagram. For example, like this is first initially I'm going to provide the clock. Okay. Clock. So whenever the negative edge occur, what happen? Your flip flop, what happen? It's going to react. This is a positive, this is a negative, this is a negative, and this one is a negative. So what is the meaning is, so for example, the initial state of the Q naught is 0. So what happened? This is Q naught, this is a Q naught. What happened? So whenever the negative occur, what happened? It's going to react. Initial state is a 0. It is 0. What happened? It's going to react. So it will retain the same state up to it encounter the next negative H trigger. So here the negative H trigger is occur. What happened? So this is a 1. Okay, what happened? It will okay, it down the value 0. Okay, again negative 1 H trigger is occur. What happened? Down the values. Okay, again one negative H triggers occur. Okay. Okay, this is called as a 0 and this is called as a 1. 0 and 1. Okay, what about Q naught bar? Okay, what about what about this is a Q naught? It going to produce a two output. One is called as a Q, another one is called as a Q1. So what about Q1? So what about Q1? So Q1, okay. The initial value of Q1 also initially is 0. Here what happened? This is a clock for second clock pulse. This is a clock for second flip flop. So when it going to operate, whenever the negative H trigger is occur, this is a positive, this is a negative, this is a positive, this is a negative. So when it going to operate in the sense, whenever the negative H trigger has occur, then only what happen it's going to operate. Okay, this is a 0, this is a 0, this is a 1, this is a 1. This is a 1. Okay, so this is otherwise called as, this is otherwise the 2-bit up counter otherwise called as, okay, otherwise called as, okay, mod 4 counter, mod 4 up counter, mod 4 counter, otherwise called as a mod 4 counter. So why it is called as a mod 4 counter? It going to it going to generate 4 output state. That's why it's called as a mod 4 counter. So one more name also is there. That is called as a divide by 4. So divide by 4 counter. I will tell you why it is called as a divide by 4 counter. Okay. Already I said the one clock cycle is nothing but one clock cycle. Clock cycle is called as one positive edge plus one negative edge. One positive edge, one negative edge. We call it as a one clock cycle. Okay. So if we consider the first thing, okay, this is called as a one positive edge, one negative edge. This is called as a one clock. Okay. This is called as a one clock. Okay, this is called as a one clock. So what about second thing? This is one positive edge appear here, negative edge occur. This is treated as one clock. So okay, this is, that can be represented as 2t. Okay, because 2t accumulate. Okay, it's going to consume two clocks. Compare with the Q. That's why it's going to denote it as a 2t. So what about next next for Q1? This is one positive edge, this is one negative edge. How many number of t is going to accumulate? This is one t. Positive, one positive. Okay. Okay, that can be denoted as, okay, this is one negative, this is one positive. Okay, this can be denoted as 4t. Compare with Q. Okay, that's why it's called as a divide by 4 counter. That's why it is called as divided by 4 counter. It's okay? It's okay for you? Do you have any queries? Akash?
Clear, sir.
Clear. Okay. It's a time for next class. So now I'm going to take the attendance. Okay, if you had any queries to be stay on online, otherwise you can wind up the session. Thank you.